Hello everyone, today we are on the tracks of Helium-3 and how the global world market of Helium-3 might be depleting or impacted and potentially a solution to that. So if you are interested in that, if you want to understand what Helium-3 is, why Helium-3 is important in the context of quantum technology or other future technologies and what role it actually plays, and a little bit about the solution, then stay tuned because today we are looking at a hidden champion called Kiutra, and before we dive into them, we talk a little bit about Helium-3. And with that, let's get started. So if you have watched some of the previous videos from the Hidden Quantum Champion series, and if you haven't done so, please check out the YouTube channel, then you know that for these chandelier type of setups, you always kind of need a cryostat. So the chandelier is part of the cryostat. It is being used for spin qubits, for superconducting qubits, and for many other technologies that require low temperatures. Now, the cooling capacity of those is pretty limited. So if you're looking at the lowest temperature stage, you're going down to microwatts of cooling power, which is okay because on the chip you don't dissipate too much heat because you're working with very small signals. But on the other hand, you have more and more cables coming down there that were transporting heat down, and the signals, of course, also transport heat down. So that becomes at some point a scaling problem. And we've seen that if we are looking at superconducting qubit systems maybe 10 years ago and compare them to today's state-of-the-art superconducting computing systems, we see that the approach of scaling the number of qubits has also always been an approach of scaling the cryogenic system. So instead of having maybe a tiny cross-section like this, now we are maybe here, and they become bigger and bigger. If you're looking, for example, at what IBM is developing, they are making a super huge cryostat, and there are also other companies that are on this trajectory, also part of the Hidden Quantum Champion series. Go and watch those. Now, these cryogenic systems, they have a certain cryogenic working principle, which is using helium. And now when it comes to helium, you know this as this funny gas that you breathe in and your voice is pitching, that makes balloons fly on the children's birthday party, but it also plays an important role in cryogenics. So the first liquefaction of helium actually led to the development or the discovery of superconductivity. So helium has always played an important role. And looking at these quantum computers, it plays an even more important role because in order to reach these low temperatures, you need helium, and not only the standard helium, which is helium-4, but also its isotope helium-3. Now, what is the difference? Helium-4, so helium-4 has basically 2 protons, because helium is where you have 2 electrons in the shell, so you have 2 protons, and 2 neutrons sitting in the nucleus of the atom. Now, in theory, you can take one of these neutrons away and it will still remain a stable isotope, it will still remain a stable atom. So that's when you have helium-3. Helium-3 only has 1 neutron sitting in its nucleus, but still 2 electrons, 2 protons. This is, let's say, a widely available isotope in the universe, and it's being used by some of these big fusion generators, which we call sun or stars, to generate the light and the energy that we need as humans to survive on this planet. But on Earth, it is actually kind of limited. And here is a little bit of the story about that. So in theory, there's a certain percentage that if you kind of drill a hole into the ground and helium comes out, there's a certain percentage that is helium-3 and a certain percentage that's helium-4. Helium-4 is much more present than helium-3, so it's kind of rare, but it didn't used to be a huge problem in the very past. So when I, for example, worked in the lab, there was an old cryostat that was a helium-3 cryostat, which means there's pure helium-3 in there, of course in a completely enclosed system so that you don't lose it. And you kind of condense it, and at the end it's like a little shot glass full of liquid helium that you can use to probe your samples. Now, if you were to buy this amount of helium helium-3 today, it will cost you easily hundred thousands of US dollars, euros, whatever. So you can look up the price. Helium-3 is quite expensive. The reason for that is that helium-3 in the past used to be, let's say, widely available, but then it was discovered that it's very useful for neutron detectors. And that's when, let's say, national security agencies, like, for example, in the US, started buying this, because you can use it to detect, for example, nuclear weapons, nuclear bombs, in ports and security, in airports, in like shipping ports. And that's why the world demand at some point kind of went down. And now the price for this is pretty high. But in order for these let's say, quantum computer fridges to work, you need the dilution of helium-3 and helium-4. So you don't need as much helium-3 because it's not pure helium-3 anymore, but you still need it. And if you are growing the size of the system, you're doing that because you also want to grow the amount of cooling capability, the amount of cooling in your system, cooling power, and then you naturally also need more helium. So this is on the one side, leading to a point where like you have the national interest, safety and security interest, kind of buying into that. You have the quantum computing industry consuming more and more of this as we scale the number of these cryostats. Then on the other side, there's also the whole story about fusion. I told you before that this big fusion reactor that we see up in the sky, which we call Sun, is using helium-3 partially to produce the energy. And actually, we want to mimic this also on Earth. So there are companies that are set up to generate or to work on fusion generators, which will be a very great way to produce clean energy on Earth. And helium-3 is an interesting isotope for that. You don't need huge amounts because by this fusion reaction you generate a lot of energy, but still you will need it, and it will be burned off. So that will of course make the situation even worse. And there are of course ideas how to solve that. If you're, for example, looking at moon, this other big thing that we see in the sky, which is glowing, but only because of the sunlight, we think that there's a lot of helium-3 up there. So it is kind of mixed with the moon dust. And there are also companies already today that are planning to harvest this material on the moon and bring it back to Earth so that we can use it, for example, for fusion generators. But let's say this might be a little bit out still, and it is quite a bit of work to get up there, build something up there, extract the helium, get it down here. So probably this might also have an impact on the pricing of helium-3 on the Earth. Now, all of that said, just to kind of set up that on a cryogenics point of view, we are still very much reliable until today of helium as a kind of refrigeration solution or cryogenic solution. Now, with all of that kind of set up, let's hop into Kiutra, because they are actually saying that you can also reach these temperatures without helium. So let's quickly take a look at their website. So here we are on Kiutra's website. Simplified and fast cryogenics company and solutions. We see here in the background, we see a cryostat solution. So you see that there's like a vacuum, pressure sensor. There's some setup here for measurement electronics and probably also temperature measurements. And that is probably the loading system, what we are seeing there. Now let's quickly take a look at what they're offering. So at Kiutra, we democratize cryogenics. We provide fast and easy access to Kelvin and millikelvin temperatures to accelerate scientific research and breakthrough applications. Quick zoom out. So Kelvin and millikelvin. Kelvin is usually the scale that we use in physics to measure temperature. Kelvin is an absolute scale. So 0 Kelvin is the lowest possible temperature that in practice can actually, I think, not be reached. So we can only go infinitesimally close to that. And 1 Kelvin is 1 degree Celsius. So 1 Kelvin is 1 degree Celsius. Millikelvin is then 10 to the minus 3 above the absolute zero temperature. And millikelvin is the range that we need in order for these quantum chips to work. Kelvin is basically where superconductors are working. 4 Kelvin is the temperature of liquid helium at atmospheric pressure. If you are pumping on it, if you are removing pressure from it, kind of inversely to your high pressure cooker, if you are sucking on the helium, you can actually reduce its temperature to about 1 Kelvin. And then from there, you need helium-3 to go. Usually, you need helium-3 to go to this millikelvin area. Now, let's see how they are doing it, right? We paved the way for tomorrow's commercial quantum technologies by making cooling scalable through magnetocaloric refrigeration, which eliminates dependency on critical resources such as scarce helium-3. We see here the L-type rapid, so super fast characterization cryostat for sub-Kelvin and Kelvin temperatures. Speed up your development cycles with the fastest cryostat on the market. Empower your team with a fully automatic cryogen-free system. Take advantage of the versatility of a modular platform by configuring the device for your specific use case, and 50 millikelvin to room temperature is the temperature range. Speed up development cycles, that's maybe also important to mention. So I have worked with these dilution refrigerators that are being used, these chandeliers that we see. And usually in order to kind of drive this down from room temperature, that will take you a day, 2 days, maybe 3 days, depends on what system you have, how fast it is actually cooling. And the companies have realized that this is quite a long time, especially for research, because if you realize you put the chip in there, it doesn't work, then you have to warm it up, put the next chip in there. This is easily a week gone for 2 chips, and maybe 10 chips don't work, right? So you're just like warming up, cooling down. So they have developed a way to do like a quick exchange mechanism, which then only takes you a couple of hours. But for that, the cryostat is kind of kept running in a certain preservative state. You have to install vacuum pumps, pull stuff out, put stuff in. It's quite complex. And when you do it as a PhD student for the first time, I think you are sweating because you are like nervous that you're doing something wrong, because it's quite a complex procedure still. So this one here seems to be a bit easier. Of course, also mentioning that on the cryogenic side, like on the helium side, there has been a lot of UX improvement if we're looking at the other companies that have been looked at in this Hidden Quantum Champions playlist. So then they also have cryogenics as a service, full service characterization, measurements, and infrastructure rental. So save on purchasing and operational cost for cryogenic equipment, temporarily add capacity when you need it, benefit from experience of our engineers and physicists. So they also offer you to cool stuff down for you as a service. And I think this is especially interesting if you're thinking about these companies that are, let's say, supplying cryogenic electronics and stuff like that. They always need to test their stuff at low temperatures. And here, for example, such a cryogenics as a service model could be interesting, whereas probably for the quantum computing companies, they need to own it because they are, let's say, driving this infrastructure, maintaining this infrastructure, right? There it's more about like load balancing, and maybe if you have a high load test requirement, then this could be interesting. Let's also quickly take a look at this. So platforms and testbed cryostats, modular and compact environments for cryogenic research and device operation. So there's the S-type, rack integrated sub-Kelvin platform for continuous cooling without helium-3. The S-type optical, so sub-Kelvin platform with optical access and low vibrations, ultra-low vibrations. And the T-type optical, so optical Kelvin cryostat, optimized for trapped ion chips. Quick zoom out, so S-type is probably which you want to have for your, let's say, qubit kind of setup. The optical one here is then when you're doing coupling experiments, if you want to have something that is superconducting maybe and optically effective. We also have to talk a little bit about magnetics later on, but let's not think about this for now. And then there's this optical Kelvin cryostat for trapped ions as well here. Then you can see here that there are also customers already. You see that there's customers in the space of universities like Chalmers, but you also see, for example, EMPA, Material Science and Technology. You see that there are research places, research centers like the Fraunhofer, IPMS, and the Forschungsneutronenquelle Heinz Meyer Leibniz, FRM II or 2, I guess 2. Leibniz Institute for High Performance Microelectronics, IMEC, which is very big here in Europe as well, the Niels Bohr Institute, but also universities in the US like Purdue University, or here Quant and others, University of Rochester, and so on and so forth. Weizmann Institute of Science as well, Walter Meissner Institute, Walter Schottky Institute. So many research places that are already working with this. Then it says, shaping the future of quantum technologies. We actively push innovation through research projects in cryogenics and quantum technologies. Lemon focuses on developing a scalable helium-3 free cryogenic cooling solution capable of reaching millikelvin temperatures. By pushing the limits of CADR, Lemon will meet the increasing cooling demands of quantum technologies, especially in quantum computing, and then Cryofast aims to democratize access to sub-Kelvin temperatures by providing researchers and developers with professional testing and characterization services at a centralized facility for advanced cryogenic measurements on sensitive devices. Then, of course, there's a way to contact them. The company is based in Munich, out of Germany. Now, let's quickly check out the technology so that we also understand this a little bit better. So here it says the core technology is adiabatic demagnetization refrigeration, short ADR, how magnetic cooling works. So a typical ADR configuration consists of a pre-cooling unit, typically a closed circle cryocooler, a heat switch, a superconducting magnet surrounding a solid-state cooling medium, and a sample platform. At the beginning of the ADR process, the heat switch connecting the ADR with the pre-cooling unit is closed, and both the cooling medium and the attached sample stage are cooled to the cryocooler base temperature of about 4 Kelvin. Usually that one works with helium-4 or just with helium, right? Then, while the heat switch is still closed, the cooling medium is magnetized by driving a current into the superconducting coil. The heat of the magnetization, is released and dissipated in the main thermal bath provided by the cryocooler. Therefore, and now that is important, right? So heat switch is closed, cooling medium is magnetized with a superconducting coil. So there is let's say a circular magnetic activity happening, and that is of course a problem when you think about superconducting chips. So you have to kind of make sure that they are shielded well from this cooling mechanism, because you are driving up a superconducting coil there, you are magnetizing some medium, and that doesn't happen in a static way, but it's more like dynamic. So you are doing this, then you're running through the cycle and you're repeating this. So there is this, let's say, magnetic kind of disturbance in the system that you have to shield your quantum computer from, because otherwise you're running into an issue, right? But let's hop back into the mechanism. So, therefore, after the maximum magnetic field has been reached, the cooling medium will return to its base temperature. The entropy of the system is now essentially determined by the magnetic contribution of the spin subsystem of the cooling medium. Then the heat switch is opened to break the thermal connection between the pre-cooling unit and the cooling medium. By reducing the magnetic field adiabatically, the temperature of the cooling medium drops, thereby cooling the attached sample stage. Usually the medium is not completely demagnetized. Instead, the magnetic field is tuned to settle a target temperature, and the remaining magnetic field is used to compensate for heat leaks from radiation, the support structure and wiring, as well as heat generated by the experimental setup. Thus, by further reducing the magnetic field, the sample temperature can be stabilized with high precision for a limited period, the hold time, which is typically several hours. Once the magnetic field has been reduced to zero, the ADR process can be repeated. The time to regenerate, usually to remagnetize and relax the cooling medium, will usually be 1 to 2 hours, resulting in a typical duty cycle of 70 to 95%. Now, let's take a quick step back. So you have this, how does it actually work, right? So you are using a material and you're magnetizing that. Magnetizing means it has some magnetic properties and you are aligning its spins, right? Similar to when you take a nail and you take a magnet and then you're moving the magnet along the nail, and at some point the nail has a magnetic property, so it also becomes a ferromagnet, similar to the magnet that you are having before. You are aligning the spins or the magnetic domains, we say, within the nail in the direction of what you are moving the magnet into. Now, if you would heat up, for example, the nail to a certain temperature, this magnetic property would kind of get lost. It would randomize again, and then you could basically start from scratch again. You can also hit it on the floor a couple of times, and then these domains will also lose their orientation. Now, this alignment of the spins is an entropy, let's say, process. So you are basically ordering the system. Entropy is the order of a system. So usually in my home, when I'm not cleaning up, the entropy kind of increases. The stuff is kind of spread everywhere. And if you then order things, it changes the entropy again, right? And now if you are looking at the microscopic properties of your magnetic material, it's the same thing. You are aligning all the spins in one direction. And then again, if you would heat up things, at some point the thermal energy becomes high enough, and then things start to kind of misalign again and they randomize again. So nature always wants to move into this misaligned state. It's a similar thing when you drop an egg. Usually it will not come back and come back into its original shape again. It will just stay spread all over your floor. So entropy only goes in one direction. It's usually making things less ordered. Now, the same is true for temperature and energy, for temperature and entropy relation in a way. So things that are highly ordered, they can, by the influence of temperature, get less ordered. And if you are now thinking about this cryostat, you're putting the material in a very ordered stage, then you're connecting it with something that has a certain temperature. And now the temperature starts to kind of remove the order from the system, so randomize the spins again. And by this, the overall temperature of the system goes down. So that is kind of the concept, the principle that is being employed here. And that's why you don't need helium, because it works using magnetics. And there's also some, let's say, presentation here or some video that kind of explains the concept. So you see, you are using this magnetic field, you are aligning those spins with the magnetic field. Then you see the heat switch here in between. And now when you're turning, I think here, you're turning down the magnetic field. Now you can see that the temperature basically misaligns those spins. And then when you're turning on the magnetic field, you can see this cooling effect here. So this is explained here in the graph as well. I think it's quite quick, so maybe if you want to understand it in detail, go and check out the explanation here. So CADR, continuous adiabatic demagnetization with filtration, how to provide long-lasting sub-Kelvin temperatures without cryogens. To provide continuous cooling without cryogens, we consider a system with two ADR units where, similar to the conventional one-shot ADR configuration, the first unit is connected to the main thermal bath with a heat switch, but this time a second ADR unit is added. It is connected to one end of the first ADR unit using another heat switch, and on the other end of the sample stage. As shown schematically, the two independent ADR units will work together to extract heat from the sample stage and to pump it into the 4K main thermal bath. Besides this serial two-stage configuration, many different CADR layouts with multiple ADR units can be realized, including serial or parallel configuration and even combinations thereof. The optimal configuration depends on the demand of the experimentalist and the specific experimental conditions. So this is kind of a different setup here. You see you have these two units, and then I guess you can see later on here that this leads to a more continuous temperature level within the sample stage because of the setup. So this is, I guess, shown here with this sample stage temperature, which is more or less constant. And that is to show that, okay, if you're using the technology in the correct way, you can also provide a stable low temperature, which is required for these kind of quantum applications. Then it also says here automatic operations, so turnkey cryostats. We believe that innovation and user-friendly design should be an essential part of cryogenics. We are devoted to manufacturing highly automated cryostat systems that can be operated without expert knowledge because they don't require liquid cooling media in the cooling process. Our cryostats are very robust and fully automatic. All systems can be controlled using a modern, user-friendly graphical software that can easily be adapted to your preferred measurement equipment and setup. And maybe also kind of to step back here and talk about my own experience. Yes, it is important to kind of make it automatic because it makes the onboarding and research quicker. And also if you're thinking about driving these machines in data center type of setups, you don't want to have a physics PhD sitting in the data center operating these systems and monitoring these things. So it needs to be automated. This is also possible with the, let's say, cryogen systems that are using Helium-4 and Helium-3 and the mixing and the dilution systems. But, and that's I think also important, of course, the maintenance is a bit of a different one because you have much more mechanical wear and tear probably in there because you have gas that is constantly circulated. That means you need pumps that are rotating like a turbomolecular pump. That is constantly driving. And I mean, of course, these things are optimized in a way. There's like, I don't know, the turbomolecular pumps, they have a very high quality nowadays. But of course, there's also some wear and tear. And if you had a system like that, you might not even need that, right? And okay, they also say they have here an automatic sample changer, which is similar to other ones that we've seen. Then there are also some R&D projects that have been mentioned already before as well. There's also the Millennium Quantum. I think we haven't seen that one, but I see here the Quantum Flagship logo. So Kiutra is providing the cooling platform for the Millennium project, a collaboration of 14 academic and industrial partners across Europe to advance trapped ion computers. And then also there's the glossary down here. Besides that, there's also the solutions. I think we've already talked a little bit about those. So here you see the L-type system, and I think we mentioned those already before. What is interesting here is you can see the base temperature, which can be down to 50 millikelvin and the turnaround time of 4.5 hours. But again, I think there's this dual idea where you can then kind of keep the temperature constant. There are also application notes available here as well. And then testimonials and so on and so forth. A lot of questions and answers down there. So cryogenics as a system, so an as a service approach, platform and testbed cryostats, and free discovery is available here as well. So put our products on the test, our exclusive offer, free discovery call, apply for complimentary test run, and limited space available. So here you can apply for a space in this program to kind of just try it out, test it. Probably it's worth, or it could be worth the effort, right? Now quickly about the company. So who we are, as per usual, we also want to see that. So we unlock the full potential of quantum technologies with our pioneering cooling solutions. Quantum computing has the potential to solve some of our most complex problems today. It will make possible breakthroughs in areas like drug development, battery technology, and climate modeling. Novel quantum technologies will also enhance our sensing capabilities, supporting applications in medical imaging and enabling physically secure quantum communication. Quantum devices can already be fabricated in large quantities using state-of-the-art thin film deposition technology. However, the development and operation of such devices require extreme environments at temperatures well below 1 Kelvin, which is minus 272 degrees Celsius, these sub-Kelvin temperatures are usually generated by helium-3 based dilution refrigeration, a method that is extremely challenging, requiring both experienced personnel and a complex infrastructure. Therefore, the use of dilution refrigerators leads to tedious low-temperature investigations and slow feedback on device properties and quality, ultimately slowing down quantum R&D. While the reliance on dilution cooling currently only slows down innovation in quantum research and information technology, the scarcity of helium-3 could ultimately stop progress entirely. Helium-3 is one of the rarest resources on Earth and produced in small volumes from radioactive tritium decay in mostly military facilities in Northern America and Russia. This limited availability threatens the sovereign use of quantum technologies and will hinder their advancement and adoption on an industrial scale. Because we believe that cryogenics could accelerate quantum technologies, not hold it back, we have dedicated ourselves to setting a new standard. This standard is characterized by high performance, fast delivery, absolute reliability, and unmatched efficiency. Central to this is the use of a fundamentally different technology in our cryostats. To reach sub-Kelvin temperatures, we cool with paramagnetic solids in a process known as adiabatic demagnetization refrigeration (ADR). ADR is well established, but we are the only company worldwide that can offer it in a continuous configuration (CADR). With this, we offer the only alternative to helium-3 based cooling. Magnetic cooling offers several advantages. Our cutting-edge cooling solutions are easy to use. You don't need to hire low-temperature physicists to run your cryostat. The systems are modular and fast, resulting in time, energy, and cost savings. And then there's also some explanation where the Kiutra comes from. So physical formula symbol of heat is the Q, and then Tura, tra, as in Latin, draw, extract, extraction. Okay. And then again here, I guess we see one of the founders together with the system L that we've talked about before. So this is not just renderings or stuff that is an actual product already. Here it says advanced cooling solutions enabling the development, characterization and testing as well as the operation of quantum systems, and then shaping the future of quantum technologies. We actively push innovation through research in cryogenics and quantum technologies. And then we see the leadership team here with the 3 co-founders of the company, as well as the board advisory here with people from industry, like for example we see Trumpf Venture, which is in Germany from industry giant Trumpf, but also Verve Venture, for example, High-Tech Gründerfonds. So a lot of people with various different backgrounds. We also see TUM here, TU Munich, so academia as well, which is, I guess, very good to have. Then there's also this little tour through the office that they have in Munich. And again, down here, a list of the supporters. We again see Trumpf, High-Tech Gründerfonds, Verve Ventures, and others like Apex Ventures, as well as public founders like the European Innovation Council, the German Ministry of Education and Research, the European Union itself, and KDT, JU, as well as Eureka, and so on. There are also network and partners down here. So you see, for example, already the QBN, so that's the Quantum Business Network, the Quantum Industry Consortium. So they are already present in those consortia where you see all the, let's say, quantum technology companies inside. Then there's also a little story or timeline of the company. So at 2018 it was established as a spin-off of the Technical University in Munich. Seed funding round was in 2019 with the first rapid characterization cryostat installed. 2020 they were awarded and the first optical cryostat was installed. Series A funding in 2021. Then in 2022 we see the first cryostat installed in the US. amongst other stuff. In 2023, we see the S-type optical model and 50 plus employees, and also awarded the EU grant. And then 2024, L-type rapid sample pack 55 is released, many different awards as well. There's also some note here on the sustainability aspect of the company, and then of course some links to their social media. Now with that, I want to already call it the video for today. I hope you liked that little excursion around the topic of Helium-3 and alternative technologies for cooling. I personally found it very cool. Of course, I needed to make that one. If you don't want to miss out on the next one, and if you stay tuned all the way towards the end of this video, please make sure to also subscribe so you don't miss out on the next video. Until then, bye bye.